Hi. So are there any questions in the last class? Whatever we discussed in the last lecture?
Yes, ma'am.
Yes, tell me.
Yes, ma'am. Ma'am, we have studied modified Newton method for roots of multiplicity, and then we have shown g prime x star is 0. But ma'am, you told me that g double prime x star is not equal to 0. That it may be 0 for some function.
So
I have checked.
see, when we derive a theory, we just check for any general function what is in hold, right? So if you have, suppose, for example, you have seen the Newton's reduction method, the error formula is what you get as convergence is f double prime of the x star divided by the 2 into f prime of the x star, right? So what is the assumption is that f prime of the x star is not 0, right? So f double prime of the x star, we, for a general setting, this means that for general function f, f double prime f x star might not vanish, right? So if you forget about the modified one, you actually see the actual Newton-Raphson method. So there we also have the f double prime of the x star divided by the 2 into f prime of the x star, right? Only assumption which we took there was the f prime of the x star is not equal to 0. Okay, so for any function f, you cannot say that the derivative of f at x star will vanish, right? Until unless it is a root of multiplicity higher than 2.
Yes, ma'am.
Right, so when it vanishes, this means that you have a multiplicity. Suppose you are having the f double prime of the x star is equal to 0. This means that you have a multiplicity at least 2, right? Greater than or equal to 2, basically.
Yes, ma'am. Then I am asking, it may have order more than 2 also, na?
So it might converge faster than if you're having the information that it is a root. So what we derived is that for any general f, if f is having a multiplicity of order m, then the Newton-Raphson method will have a quadratic convergence. Okay, so we derived the result for any general f. Now for some specific f where you have it, say if it is derivatives are further vanishing, you can use again the fixed point iteration method, and you can try to derive what is the order of the convergence you can expect for this. But for any general function f, Newton-Raphson method will converge with the quadratic rate. Okay, so that's what we proved in the last.
It means theorem just says lower order, like इतना तो order आएगा, इससे ज़्यादा भी आ सकता है.
No, for general f, you will get a quadratic convergence, right? Now, for some specific cases, you can observe faster convergence also. Okay, so it says that the quadratic rate, that is what you're going to observe when, see, you just try to observe the error formula, what we get it. Okay, so just try to write down and then try to observe that what is the error formula, what we are getting. So that will tell you that whatever the case you're discussing, you just try to write down that if we have those conditions, what is the error we are expecting. So accordingly, so if you're familiar with the MATLAB, right, you can try to take some function for which whatever the phenomena you're observing, that is happening, and you just try to implement it in the MATLAB and try to see what is happening, whether what you're observing is the same as theoretical things or not. Okay, just that's the quick way to verify that, okay, so if you want to observe certain phenomena with certain specific conditions, you just try to, it's a few lines code in the MATLAB, and then try to observe it, that what is happening. Okay. So what theory, when we derive it, we just work it with a general setting that under these assumptions on the function f, this is what we observe. Okay. So we'll see if we can, if we get time, we will try implementing these methods in the MATLAB and try to see how they behave on numerically, like whatever we have seen theoretically, whether it coincides with my theory or not, right? So these things we will try to verify using taking some functions and see what is happening when we implement it. But for now, if you want to do it, you can just take it as an exercise and try to do it. And specifically try to observe whatever the conditions you are telling that, okay, if I assume this, then this is what is happening, right? You can always construct some function f for which whatever the phenomena you're observing, that will happen, and try to see what is happening to the convergence of the Newton-Raphson method. Okay.
Okay.
And in the interpolation part, what we basically just prove that. So suppose we have the data as xi, yi's. I is equal to 0, 1 up to say n. That is, we have n plus 1 data points, right? Then there exists a unique polynomial of degree less than equal to n. So let's call this polynomial as Pnx. So n is denoting the degree. Which interpolates this state. That is, we have that Pn at xi will be equal to yi for all I is equal to 0, 1 up to n, right? In fact, we found the explicit form of the polynomial also, right? We saw that Lagrange form of the interpolation. So this is the Lagrange interpolation. So what is the Lagrange form of the interpolating polynomial? So we have Pnx has this representation. We can write this as Pnx is summation of Lix into yi, where I is running from 0 to n. And what are these functions Lix? So Lix are, so for each I, we have Lix as, so these are the products of, so if I'm looking at the Li for a fixed I, then I will have the product of all x minus xj except x minus xj. So this will, j will vary from 0 to n and j not equal to I. And we have a division by xi minus xj. Right? So this is a Lagrange form of the interpolating polynomial. So this is Lagrange interpolating polynomial. And we call these as a Lagrange basis polynomial. Okay, and you can quickly observe. So basically, you can see the Lix has all the factors x minus x1, x minus x2 up to x minus xn, except the factor x minus xi, right, in the numerator. So if I evaluate Lix at x is equal to xj, suppose I fix my I, and if I evaluate Li at some xj, so you can observe that this is the same as delta ij, which is 1 when I is equal to j, and 0 when j is not equal to I. Okay, because when you will substitute xj, and x minus xj is a factor there for j is not equal to I, so Li xj will be 0, and when you will substitute xi here in Lix, then you will see that numerator and denominator both are the same, so you will get 1. Okay, so this is a very important property of these Lagrange basis polynomials. So we will exploit this as we proceed further. Okay, now let's try to, so we have got an interpolating polynomial. Now let's try to take one example and try to observe what happens. So here I'm going to take an explicit function. Suppose I know the function explicitly. Let's take the exponential x. So let the values of function, which is the exponential function, suppose we are given the values at 2 points. Say x naught is equal to, so let me take some values, 0.82 and x1 is equal to 0.83, and the corresponding values are y naught is equal to 2.2705 and y1 is equal to, so let me write the value explicitly. So this is 2.293319. Okay. So what we have to find is the approximate value of f 0.826. Okay. So here I have given you the function explicitly, but suppose the function f is not known here, even then you can do this exercise, right? Because we have learned that we can design a linear polynomial using these 2 points and find the approximate value, right? But here I've given you the function explicitly. So basically you can use take the help of calculator to really simply to work out all the calculations. But let's write down what is a polynomial which we will be able to get using these 2 values. So we are given x0 and x1, that is 2 data points we have it. So we can find the linear interpolating polynomial. So which is given by, we will have L0 x y0 plus L1x y1. So which is basically, so L0 x is x minus x1 divided by x0 minus x1 times y0 plus x minus x0 divided by x1 minus x0 into y1. So now x0, y0, x1, y1, they are given to us. So you can substitute here and you can simplify it. So I'm directly writing it, what is the output after upon simplifying. So we will get this as 2.2819 times x plus 0.39934. Okay, so now we have found a linear interpolating polynomial, so which is basically a approximation of the fx. So I can find the approximate value of 0 at 0.826 as by evaluating p1 at 0.826. So if you evaluate this, you will get it as, so let me write, so this is 2.28419. This is what we get. Okay, now since we know f explicitly, right? So fx is given to be exponential x. So you can also find the explicit value of this function at 0.826. Okay, so this is going to be 2.2841638. So I'm doing the rounding here. Okay, I'm not writing the further digit. I have done the rounding here at this point. So let me write this as an approximate because I'm just truncating it at this 7th digit here. Okay, but this is this approximation I'm writing in the sense of the rounding here. Okay, so we have the exact value of this exponential function here at this point 0.826, and we have found an approximate value using the interpolating polynomial, right? So you can see that the 4 digits up to the after the decimal, they are the same in both the functions, right? So this is what the approximate value we get, and then you can see there's a like it approximate up to the 4 digits after the decimal, which is correctly, right? Now let's try to observe that what happens if I increase the polynomial degree. That is, suppose I include one more node point, which is x2 is equal to 0 point. So I've taken 0.82, 83, and then 84. Okay, and the corresponding value, let me take it as, so this is y2 is so this is 2.316367. Okay, this is the given value, suppose we have it. Okay, so now we have 3 data points, x0, y0, x1, y1, and x2, y2, right? So we can design a quadratic interpolating polynomial. So you can write down what is p2x. So p2x is going to be summation of lix into yi. I is equal to 0 to 2. So you can find out what this polynomial is because the data is given to us. And what I'm interested at, what will happen when I substitute x is equal to 0.826 here. Okay, and you can find this polynomial and you can substitute x is equal to 0.826, and what the output I get it as. So this is 2.2841639. Okay, so you can see that here so after the decimal, how many digits you have, which is the same as the exact value. So you have the 6 digits which are same as the exact value of the exponential of 0.826, right? So this means that as we increased the number of the data points, or thereby we can see that we have increased the degree of the polynomial, which is approximating the fx, then we have got a better approximation, right? So in fact, you can observe that if you finally, because you know you can increase say x3 and x4, you can find the cubic and say the 4th degree polynomial, you will get a better and better approximation of the exponential of this. So here you don't truncate it, you just write down the exact value of the exponential. Okay, and you will see that as you increase the polynomial degree, you will get a better approximation of the exponential of evaluating it at any point. Okay, so what impression this gives, that does it always happen that if we increase the polynomial degree, that is if we have a more data points, we get a better and better approximation. So let's just write it as a remark. So what is the impression we are getting out of it is, so this example gives the impression that if we increase the data points, the number of data points, that is the number of nodes, and thereby we are increasing the polynomial degree, so then this polynomial approximates the original function more accurately. Right? This is what the observation we can make from here. For example, if you try to just implement in the computer and just take the function as exponential of x and write the code for any general n and just try to increase the values of the n 1, 2, 3, that is increasing the polynomial degree, and you can observe that it will approximate the number of digits which will match exactly in the exact value that will increase. Okay, so but this phenomena is not true in general. Okay, so this is happening. We can observe this for this example. So in general, this is not true. And we'll try to justify it that why it is not true in general. But this phenomena, like you can get a better and better approximation by increasing the polynomial degree if the function is smooth. Okay, so you can see here the function is exponential function. So it is a C infinity function. So you can, as you will increase the polynomial degree, you will get a better and better approximation. So what is going to be the behavior of the polynomial approximation, it also depends on the smoothness of the function. So we will see that in this result. So basically what we have to analyze the error, right? That what happens if you are approximating the value of the function at any point x by the interpolating polynomial. So what is the error we are getting, right? So let's try to obtain the interpolation error. So this is for the Lagrange interpolating polynomial. So let me call it Lagrange interpolation error. So I'm going to state this as a theorem. Okay, so I will be requiring this notation here. So I've used this before also. So this is a H, and I'm taking A1, A2. You can have as many points as you want. So this is the notation I'm using for smallest interval containing all these points, A1, A2 up to A1. Okay, so which means that you take a minimum of these numbers, that will be the lower value of the interval, and then you take a maximum, that will be the upper value of them. So you will have the interval, say if you call it AB, A is going to be the minimum of all these AIs and B is going to be the maximum of all these AIs. So let's take the data, the nodes as let x0, x1 up to xn. These are the distinct nodes. And let f be a given real valued function with n+1 continuous derivative. Now, where I'm assuming that this is n+1 times continuously differentiable, this is on the interval. Let's call it, so I'm taking the smallest interval containing x0, x1 up to xn, and so I'm supposed finding the error at the point t. Okay, so let me denote it by it. With some t okay, that is, suppose we are given the n+1 data points And what we are interested in finding the value of approximation of the function f at the point t. Okay, so we are going to analyze that what is the error we are going to commit when we use the interpolating polynomial. So we can prove that then there exists, let's call xi, which is in this interval it, such that ft minus summation of j is equal to 0 to n f of xj, lj evaluated at t, this is given by t minus x naught, t minus x1 up to t minus xn divided by factorial n plus 1 into n plus 1th derivative of f evaluated at the point j. Okay, so if you observe that this is nothing but the interpolating polynomial, let's call it Pn, and this is at the point t. Okay, so basically this is nothing but your interpolation error, that ft is the exact value of the function and pnt is the value what we are getting using the interpolating polynomial. And what this theorem says that the interpolation error at the point t is given by this expression. Okay, and you can observe here that this is not just depending on the x naught and x1 up to xn, it also depends on the n plus 1th derivative of the f. That is, it also depends on the smoothness of the function f. Okay, so let's just try to prove this theorem. So note that what happens if t is any of the node points. Suppose t is equal to some xi for some I. Then what will happen? Does this result hold? So what will happen to the left hand side? So let's give it a equation number here. So I think this is 2. Then what is going to happen to the RHS of 2? So T is one of the node points. So this is 0. And what will happen to the LHS?
0.
So we will have that f at xj minus xi minus j is equal to 0 to n f at xj lj at xi. So what is going to be this quantity? So what is the property of the lj? So here I'm running I is fixed and then we are running a summation over j. So whenever j is going to be equal to I, this is lj of the xi will be 1. At all the places, it is going to be 0, right? So this is nothing but, so
fxi.
yes, so when you will take j is equal to I, you will get, this will be f of xi and lj at the xi will be 1. And at all the other places, it will be 0. So you in this summation, you will get only one term, which is f of xi, right? So this is also 0. So f of xi minus f of xi, so we get it 0. So if t is one of the nodes, then this relation trivially holds, right? So therefore, this result, or let me call this listen to, this holds trivially if T is any node point. So what we are going to assume now that T is not equal to any of the node point, and then we are going to see what will happen to the interpolation error. So assume that T does not equal any node point. So then we will try to prove that ft minus pnt is going to be this expression. Okay. So let's try to denote the error by some function. So I'm taking fx minus pnx, where pnx is summation of f at xj into lj of x. J is running from 0 to n, and here lj's are the product of. So I'm taking j here, so I'll take the product on the i's. So x minus xi divided by xj minus xi, and I is running from 0 to n, and I is not equal to j. Okay, so let's call this as a function ex. So ex is basically the interpolation error at the point x. So what we can observe for ex, that if you evaluate e at any at the xi, this is going to be f of xi minus pn evaluated at xi. So we have already observed that the interpolation error is 0 at all the node points. Okay, and we are interested in finding the interpolation error at the point t. So now what I'm going to do, I'm going to construct one function using this function ex, which not just vanishes at the xi, but also vanishes at the point t. Okay, so let me call that function as gx. And I'm going to use my ex to construct this. So I already know that e at xi's are 0 for all the i's, right? So I want this function g to be 0 at t also. Okay, so what I'll do, I'll just subtract some term here times e of t. Okay, so if eventually if this function, whatever the function we will have here, if this function takes the value 1 at x is equal to t, then g at t will be 0. Okay, and what I want, that g at xi should also vanish. So what I should multiply here? So at this point, e at xi will be 0, but this contribution also has to be 0, second term. So I'm going to take here so if I define my psi x as x minus x naught, x minus x1 up to x minus xn, then I will take here the factor psi x, because it will be 0 at x is equal to xi, and I want this factor should be 1 at x is equal to t. So I will divide by psi t. Okay. So let's call it 3. So we are defining this function. Now what we can observe, so first observation we have made that g at xi, this is equal to 0 for all I lying between 0 to n, and g at t is also 0. Right? Now what more we can observe for this function g? So what is given to us, that f is n plus 1 times continuously differentiable. right? So what can we say about the function g? The differentiability of the function g? So first of all, you note that if fx is n plus 1 times continuously differentiable, e is going to be n plus 1 times continuously differentiable on the same interval, right? Because Pn is a polynomial, so it is the infinitely differentiable. Okay, so Ex is differentiable and psi x is also a polynomial. So this is also n plus 1 times differentiable, right? So this means that we will have G is also n plus 1 times differentiable. So since we have F is n plus 1 times differentiable on the interval it, therefore Gx is also n plus 1 times continuously differentiable, okay? Continuously differentiable. On the same interval it, okay? Because E and psi both are continuously differentiable. So G is n plus 1 times continuously differentiable, and we know that how many roots this has? How many zeros is
n
it
plus
has
1.
in the interval it? So from here I can say that it has n plus 2 zeros in the interval it, right? G has n plus 2 distinct 0 in the interval it. So now let's just try to imagine that you have a, let's take the points as x0, x1, suppose you have xn somewhere, okay, and t is somewhere. So what we have that G is vanishing at all these points. Okay. So what can we say about the zeros of the G prime? So suppose G has n plus 1 distinct zeros in this interval, and then what will happen to the zeros of the G prime? How many zeros the derivative of the G will have? Can you use the mean value theorem and say something? Suppose
Ma'am, n plus 1.
yes, so if G has n plus 1, n plus 2 distinct 0, then G prime will have a n plus 1 distinct 0. Because if you apply the mean value theorem, what do we have? If we apply, say, at any xj and xi, so we will have that f of xj minus f of xj minus 1 divided by xj minus 1. This is equal to some f prime of the c, where c is lying between xj and xj minus 1. Since, sorry, g here. Okay, since g of xj and g of xj minus 1 both are 0, so we will get that g prime of the c is equal to 0. And that will have, you have n plus 1 distinct points here where g is vanishing. So you will have n points for the g prime where it will vanish using the mean value theorem. Okay, so using
Ma'am, how we get n plus 2 distinct zeros for G?
this is what we have written here. So we have n plus 1 points. N plus 1 are, so we have I is varying from 0 to n, right? So we have n plus 1 points here, and t is distinct from xi.
Okay, ma'am. Okay,
That's
ma'am.
why we have n plus 2. Okay, so if we apply the mean value theorem, so then we can say that G prime will have n plus 1 distinct zeros in the interval it. And if I repeat this process, what can I say about the n plus 1th derivative of the g? How many zeros it will have? So you can observe that for any, suppose you talk about the jth derivative of g at some, so we are taking the jth derivative where j is ranging from 1 to n plus 1. Okay. So how many zeros the jth derivative of g will have? So this will have n plus 2 minus j zeros in the interval it. Okay, so you can just repeat this process. You will have a n plus 1 zeros for the g prime. Now you, for the g double prime, you will have n distinct zero, and if you continue repeating this process, what you will left with is the g n plus 1th derivative of the g has a 0 in the interval it. Excuse me. And let's call this 0 to be xi. Sorry, xi we have what? Okay, xi is the one which we are supposed to use. Say xi. That is, what do we have is that gn plus 1 at xi, this is equal to 0. So we already know what g is. So let's try to find out what is the n plus 1th derivative of the g. So we have so this is going to be the n plus 1th derivative of the e, and then I will require the n plus 1th derivative of the psi. So what will be the n plus 1th derivative of the psi? It's a polynomial, right? So you can differentiate it. Okay, so this you have to check that if you differentiate psi n, which is a polynomial of degree n plus 1, and if you differentiate it n plus 1 times, you will get a constant, and that constant is factorial n plus 1. Okay, and what is ex? Ex is fx minus pnx. So if I differentiate this n plus 1 times, so this is a polynomial of degree less than equal to n. So what will happen to the n plus 1th derivative of this function? So if Pn is a polynomial of degree less than equal to n, n plus 1th derivative of Pn will be
0.
0. So what I will be left with is just n plus 1th derivative of f. So we have here is that this is n plus 1th derivative of f minus n plus 1th derivative of psi n is factorial n plus 1. And then we have et and divided by psi t. So this is what we have, gn plus 1x, right? So therefore, gn plus 1 at xi, this is equal to 0. This is nothing but fn plus 1 evaluated at xi minus factorial n plus 1 divided by psi t into et. So this will imply that et is psi t divided by factorial n plus 1 into n plus 1th derivative of f evaluated at xi. And this is nothing but ft minus pnt, right? So this is what we wanted to prove. And psi t is t minus x naught t minus x1 up to t minus xn. Okay, so this is how the interpolation error will behave when you use the polynomial of degree n. All right. So is it okay so far?
Yes, ma'am.
Okay. So what we have seen that if we are given the xi's and the corresponding function values, let's call them yi's, then we can find the interpolating polynomial, and we have also found that how the interpolation error will look like. That is how the error will, suppose I'm taking any point x, then what is going to be the interpolation error at this when you use this interpolating polynomial to find the approximate value, right? But mostly what happens that we don't like when you're going to use the interpolation. If you exactly know the function f, you're not going to use the interpolation to find the approximate value. You will directly use the function, right? So what happens in by when you perform some physical experiments, you get the data, right? You get suppose these evaluation of the function, which we don't know what f is, right? We get these values by i's, right? And if these values are coming through some experiments, they also involve some round of errors, right? As suppose, for example, if you're using computer also, the computer also will do some rounding off, right? It does not store beyond 10 to power minus 16 or 10 to power plus 16. It cannot store the numbers bigger than that. So if the number is having more decimal point, that is a big number is bigger or smaller than this, then there'll be some rounding off happening, right? Or if you're getting the values from some experiments, so suppose you get the exact value is suppose f of xi, but then you get the value what you get through the experiment is say fi, okay? And so what is present, what is like how it differs from the fxi, it might have some round off error. Say fi is equal to, you can have f of xi is equal to some fi plus some epsilon I, where this is coming from round of error, right? So if you use these values to compute the interpolating polynomial, then there'll be some other error also present because of this round of errors, right? So let's try to see just for the case of the linear interpolation that how these round of errors really affect the total error. So I'm considering the linear interpolation. And we are just going to see the effect of round of errors. That is, so for the linear interpolation, meaning I'm considering the 2 points and the corresponding data. That is, it's called that f0 and f1. Let f0 and f1 be the measured data at the nodes x0 and x1. And let's take xi0 and xi1 be the rounding errors. And we assume that the mod of xi0 and mod of xi1, they both are less than equal to some epsilon, okay, for a known value of the epsilon. That is, I'm just taking the upper bound of both the numbers, xi0 and xi1. Okay, so here what do we have is that that fx0 is the actual value of f is nothing but this f0 plus some epsilon naught, and then actual value of fx1 is nothing but f1 plus this epsilon 1 which we have taken. Okay, so suppose I use now if I'm trying to find the interpolating polynomial, I'll be using this measured data, right? So what is going to be the error in that case? So the interpolating polynomial is going to be x1. So let me write it explicitly. So we will have it x minus x1 divided by x0 minus x1 into f0 plus x minus x0 divided by x1 minus x0 into f1, right? This is what will be the interpolating polynomial, right? Linear interpolating polynomial. Or I can just take out the minus sign here. So I can write this as x1 minus x into f0 plus x minus x0 into f1 divided by x1 minus x0. So if I see the total error, this will be fx minus this quantity. So let's call it as ex here. So now let's just try to simplify this. So f0 is f of x0 minus epsilon naught, right? So I'm just going to substitute here. So what I will get is this term and then I will get x1 minus x times epsilon naught plus x minus x naught times epsilon 1 divided by x1 minus x naught. So I've just used that f naught and f1 is given by f of xi minus epsilon I. Okay, so this is nothing but the ex, right? The exact interpolation error, so which we just derived the formula for. So this is, let's call it again. Yeah, here I'm using the capital E, and so we could have used a different notation also. So for example, I can take it as Tx. Okay, and let's call this as Rx. Okay, so where this Ex is the interpolation error. Which is fx minus, so if I call this this interpolating polynomial as p1x, then we know what is exactly this error is, right? At the point x. So we have already obtained the formula for it. So this is going to be psi x divided by, so we have n is equal to 1 here. So psi x divided by factorial 2 into f second derivative of f check. So let's write it down. So we have x minus x naught into x minus x1 divided by factorial 2 into f double prime at some xi, where xi lies between. So here we have just 2 points x0 and x1, so I can explicitly write the interval. So I'm taking x1 is bigger than x0. Okay. So I can in fact find the upper bound on the ex. So we can find that the maximum of ex over this interval. So where the maximum will be attained? So this is a quadratic polynomial, right? X minus x naught into x minus x1. So for the quadratic polynomial, so this is like you can imagine a parabola, right? So where the maximum will be attained for this function, for the absolute value of this. Okay, so you can check out that this is less than equal to, so the maximum of this function x minus x naught into x minus x1 on this interval x naught x1, this will occur at the midpoint. Okay, so you can write down that this is for any x, absolute value of the ex will be less than equal to, if I substitute x is equal to x naught plus x1 by 2, right? So this term is going to give me, so x minus x naught and x minus x1 both are going to be the x1 minus, so what is x minus x naught? So this is x naught plus x1 by 2 minus x naught. So I will get it as x1 minus x naught, and same with the second term. So I will get this as x1 minus x naught squared divided by 2 into f double prime of xi. Or I can say that, so if I call this distance between 2 points, that is the length of this interval as h, let me use it and then I'll write it. So I can say that the maximum of the ex, this is less than equal to h squared by, sorry, I will get a factor of x minus x naught, 2 I already have, and then I will get 1 by 2 from here and 1 by 2. So this is going to be 1 by 8. Okay, so this is h squared by 8 f double prime maximum of f double prime of x over the interval x naught x1. Okay, or you can use different parameters. So is it okay so far? So this is the upper bound of the ex, right? Now what is the other term we have here? We have rx is another term which we have to see what is happening with this. So what is rx? So rx is x1 minus x into xi naught plus x minus x naught into xi1 divided by x1 minus x naught. Now what will happen to the maximum of this function? First of all, if I try to plot this function, how it will look like? This is a linear polynomial, right? So what will be a graph of a linear polynomial?
Line.
It is going to be a line, right? So if I want to see the maximum of this function rx, so where, suppose we have a line, so where we'll have a maximum occurring over the line. So it will happen at either of the endpoint. It can be either on the say the suppose you have over the interval AB, and then you have some line over this interval. So either the maximum can occur at either the maximum can occur at the point B, or you can have the line where the maximum can occur on the point B. So there's only two possibilities, that either on it the maximum will occur at either of the endpoints, right? So let's try to evaluate what will happen. Suppose if we take, so endpoints here are x0 and x1, right? So what will happen if we substitute x is equal to x0 here? So this is going to be, so this term will be 0. So we will have it as j0. And if we take r at x1, so this is going to be, so first term will be 0. So we will be left with j1. So therefore, the maximum of mod rx over this interval this is going to be the maximum of absolute value of these quantities, which is less than equal to epsilon. And this is because Rx denotes a straight line so its maximum on this interval x0 x1 this is attained at the endpoints, which means that it will be either on the x0 or on x1. Okay, so what we have obtained that the total error Tx, this is bounded by the absolute value of the Ex and the absolute value of the Rx, and if we take the maximum both sides, or we can say that this is less than equal to the maximum of Ex, which we have already found the bound for. So this is h square by 8 maximum of f double prime of t over the interval x0 x1 plus maximum of mod epsilon naught and epsilon 1, which is nothing but the less than equal to epsilon. Okay, so what it says that, so suppose your round of error is going to be some fixed quantity. Suppose my epsilon is of order 10 to power, let me take some small number here, say 10 to power minus 5. Okay, and suppose if your h is of order 10 to power minus 2. Okay, then you can see that here I'm having h square factor, right? So h is of order 10 to power minus 2, so h square is going to be of order 10 to power minus 4. So this term will be of 10 to power minus 4 and this term is of 10 to power minus 5. So of course this error is dominating, right? So basically your interpolation error, whatever we have it, that is going to be the dominating factor. Okay, but suppose if my h is of order 10 to power minus 3. So if you do not take care of this round of error, you will just take it that, okay, I have h is of order 10 to power minus 3, so h square is going to be of order 10 to power minus 6. So that is going to be your interpolation error. That's what you will expect, right? But since round of error is of 10 to power minus 5, so though this term is 10 to power minus 6, but this term is still 10 to power minus 5 order, right? So this term is going to dominate. Okay, so if your epsilon, so depending on the epsilon, you might have to choose h to be very small for your interpolation error to dominate. Okay, so your round of error may be smaller, like if they are larger than your interpolation error, so then your round of error they are going to dominate your total error. Okay, so this theoretically, of course, this might not look so significant, but when you try to implement this in the computers, so this really create a huge difference, because sometimes you just look for the errors that, okay, theoretically, I'm expecting that my errors would be of order 10 to the power minus 6, but then I'm not observing the same numerically. So that there might be some round of error presents, which might really affect your total error part. Okay, so I just wanted to show this phenomena for the simple case, that is for the case of the linear interpolating polynomial. But of course, the same ideas can be expanded for the higher order also. But let's not go into the general case. So rather, let's try to look back the question the remark which we stated before, that what we observed before, that we were taking the exponential x function and we were using the interpolating polynomial p1, p2, and like that, and we were observing a better and better approximation, right? So let's try to answer that. Whether I stated that it doesn't happen in general, right? So let's try to understand that what may affect it. So let's consider the interpolation error. So which is given by fx minus pnx. This is at x minus x naught, x minus x1 up to x minus xn divided by factorial n plus 1 into n plus 1 derivative of f evaluated at some xi, where xi belongs to the smallest interval containing all these points. Okay. So now for the further discussion, I'm going to consider that these points x0, x1 up to xn, they all are equally spaced. Okay, so we consider evenly spaced nodes x shape. That is, what do we have? That xj is given by x0 plus jh, where j is ranging from 0 up to n. Okay. And let's try to consider so first, let's understand the case of the n is equal to 1, the same argument which we have already used here. So I'm just going to take the same ideas. So we have that. So if I take, so we have already seen these arguments, so I'm not directly going to write it. So if we take the maximum of the interpolation error over the interval, so h is going to be x0, x1 in this case. So what it is going to be? This will be less than equal to so let me denote the maximum of this quantity by some factor. Let's take Cn plus 1. This is the maximum of t is in. So the interval, let's call this interval to be I. Okay. So what can I write? So I'm just going to repeat the same arguments what we have seen here, right, in this part. So what I will get, that this is going to be less than equal to C2, because I'm taking the maximum of f double prime of t over this interval times C2 divided by factorial 2 into maximum of x minus x0 this function over the interval 0, 1, x0, x1. Okay, and we have already seen that this function attains the maximum value at x0 plus x1 by 2, and the maximum value is nothing but h square by, so this is going to be h square by 4, where h is nothing but the distance between x0 and x1. So what we have got here is that this is h square by 8, okay, and C2 is maximum of f double prime of t on this interval. Okay, so likewise, if you just try to visualize what will happen to the general case, right? So if I call my, so you have this function x minus x naught, x minus x1 up to x minus xn, and then you will have the n plus 1th derivative of the xi. So if I try to write the general case, just you can mimic the same steps. This will be less than equal to Cn plus 1 divided by factorial n plus 1. Maximum of x is in I, and absolute value of xi and x, where I and x I am taking it as x minus x naught up to x minus xn. Okay, and since we are assuming that these all the points xi's are equally spaced, so note that if I try to find, of course you can try to find the absolute value, but I'm happy with the upper bound. So each of the term will be less than equal to h, right? So we will have h raised to power n plus 1 as an upper bound of this. So I can have that this term is less than equal to, so the maximum of this will be less than equal to some constant times h raised to power n plus 1. So that constant I'm taking here. Okay, this sign I use it. So a is less than equal to b. This means that there exists some constant such that a is less than equal to c times b. Okay, so the constant which I will get with h I'm hiding here. Okay, because that is not going to depend on n. So for example, here you can observe that it was 1 by 4 here, right? Divided by factorial n plus 1, and then I have a Cn plus 1, which is the maximum of Fn plus 1 of t, where t is belonging in I. Okay, so if you are familiar with the L infinity norms, so this is nothing but the L infinity norm of n plus 1th derivative of f over the interval I, in case you are familiar with it. Okay, so the definition is the same, what we have written here. So now let's try to just answer the query which we raised before, that does it always happen that if you increase the polynomial degree, will the error will get reduced every time, right? So in a way we are asking that if n tends to infinity, does the error goes to 0? So can we say that this tends to 0 as n tends to infinity, right? So increasing the polynomial degree, meaning that you are increasing n, and then decreasing the error, meaning you, as you increase n, you expect that error is getting smaller and smaller, right? So the answer is not. So note that if you take n tends to infinity, of course you will observe that this term will go to 0, but it might happen that your n plus 1th derivative of the function, this term might grow up, and so that the total error might still be large. Okay, so h is not the only contributing factors here. So you also have the term n plus 1th derivative of the f sitting here. Okay, so if f is not well behaved, then if you're going to compute higher and higher derivatives, so these might increase because I'm having the maximum of n plus 1th derivative of f over that interval, right? So this term might increase so that the total, though your this term is becoming small, but if this term is very large, so your overall error might still be large. Okay, so let me just write it here. So although the term h raised to power n plus 1 divided by factorial n plus 1. So let me give it a question number. I think this is 4. In the upper bound, in 4, this tends to 0 as n tends to infinity. So if but the term, so I'm just using the same notation which I used here, but you can write down this quantity. So I'm just for avoiding to write the complete term. So, but this term might increase significantly as n increases. Which will make it possible for the, which makes it possible for the interpolation error to be a large number, right? To be high. And this you can verify using this example. So let's just take this example. So I'm taking a function from interval -1, 1 to r, and this function is given by 1 divided by 1 plus 25 x square. Okay. And you can verify that if you take, so we have equally spaced point, right? So if you take your xi's to be 2i divided by n minus 1, and you try to find your p and x using these points, right? So as you will increase the polynomial degree, that is, if you make n larger and larger, you will see that the error, which is fx minus p and x over this interval -1 to 1, this becomes, this increases as n increases. So I will ask you to just, okay, so this is, this can be well observed if you can just try to implement this method. That is, f is given to you. You just use if you can write down a code for the Lagrange interpolating polynomial, then you just you have to just change the values of the n, right? You take what is happening for the P1, P2, P3. So for example, if you will see for the P10, you will see that, okay, so for when you will find, right, so try to approximate using P10. So it will involve the 11th derivative of the function f. And the reason for this phenomena is that you will see that as your n increases, the magnitude of the derivatives is getting larger. So this is going to be approximately 4 to 10 to the power 15. Okay, so if you want to check all the details about, so there's actually a whole paper written on this phenomena. This is called the Runge phenomena. So which is basically a counterexample that if you increase your polynomial degree, the interpolation error does not reduce always. So for that, your f has to be a well-behaved function. So in this case, if you increase, if you try to see the magnitude of the higher order derivatives, as you increase the order, then it will get larger and larger. Okay. So I'm not really going to show it explicitly because that requires a further one lecture. So, but you can refer to this book. So there's a book by Isaacson. There's Isaacson and so this is E. Isaacson and H. Keeler. And this is chapter 6. So the book name is Analysis of Numerical Methods. Okay, but what I would like you guys to do, that at least you try to implement it in, if you're familiar with any of the softwares, or say if you're familiar with the MATLAB, you just try to implement this. That is, try to implement the code for the finding the Lagrange interpolating polynomial and try to observe it for this function. That what happens if you try to go to the increase the polynomial degree, that is start from P1, P2, and as you will increase it, go to the 10, 11, like that, you will see that the error really gets very high. Okay. So yeah, I think that is all for today. So we'll start. So in the next class, what we will do. So this there's a one difficulty. Okay, let me give a little motivation, and then we will end the lecture. So what we have been doing, we have been given the data points, say x, y. Suppose we are given x0, y0, x1, y1, x2, y2. Okay, so you can find a polynomial of degree 2 using this data, right? Which is, or let me take a general case. So you have, say, xk, yk, right? So you can find a polynomial of degree less than equal to k, which is going to be summation j is equal to 0 to n, Lj of x and yj, right? Now, what are the Lj's of x? These are the product of x minus x1, x minus x2, up to x minus xj minus 1, x minus xj plus 1, up to x minus xn, divided by xj minus x1, up to xj minus 1, and the next term will be xj minus xj plus 1, up to xj minus xn. Right? So suppose we have been given this set of data points and I have determined my pkx. Okay. Now suppose after knowing this pkx, suppose I have given the information about one more data point. Suppose I increased that, okay, I got the information about at one more data points. Right? So can you use your pkx to find So once we have the information of the xk plus 1, I will be interested in finding the pk plus 1 of the x. Right? So can we use this pkx to compute the pk plus 1x? That is, all the work which we have done in computing the pkx, can that be utilized to find pk plus 1x? So to find pk plus 1x, again I have to find lj of the x. But note that this time you will have one more extra factor in each of the term, right? So all these computations which you have done here, or all this hard work which you have done in computing pkx, that cannot be utilized to find pk plus 1 if you directly want to compute using this formula. Sorry, this is not n here, this is k. Okay, here k plus 1, lj of x, yj. But what are lj's of the x here? Lj's of the x will have, so here these are the products x minus xi divided by xj minus xi. I is running from 0 to k, I is not equal to j. But now you will have a product from 0 to k plus 1. Right? So you have to evaluate all these factors again. You cannot utilize that you have already computed the pkx, and then you can use that information, and then you can try to incorporate this extra information we have been given, right? So, but what you have to do, you have to again start computing all of your LJs corresponding to this new data, right? So this is one drawback with the Lagrange interpolation, that if you already know a polynomial, interpolating polynomial, and if you want to find an interpolating polynomial of one higher degree, you cannot really use the pk, like this polynomial of degree lower, to really compute a one polynomial of degree 1 higher. Okay, so we'll try to find another form of these interpolating polynomial where we can exploit this fact that if I know a pkx, then I can use this information to compute the pk plus 1x. Okay, so this we will see in the next lecture. So we stop here.